Assalamualaikum warahmatullahi wabarakatuh, and hello everyone. We are from Group 2 and today we will be presenting about our group assignment, project assignment for Mathematics 099. First of all, I would love to introduce to you guys about my team members. So we have 5 members in our team, which is me as the leader. I am Hilman, we have Dania, we have Shafi, we have Adam, and we have Shamil.
In Newton's law of cooling, our first task is application of first-order differential equation. This is used to show how a quantity changes at a rate depending on itself or another variable.
What is Newton's law of cooling? So basically, Newton's law of cooling describes that how temperature of an object changes over time when it is placed in a surrounding with a different temperature. But for our experiment, we use Meatball as our object and heat it up in a microwave for about 10 minutes. The law also states that the rate of heat loss is directly proportional to the difference in temperature between the object and its surrounding, where mathematically written as dt over dt equals to k bracket t minus ts, where t, capital letter T stands for temperature of an object, ts stands for temperature of surrounding, and k stands for constant of proportionally. Let's move on to the procedure. So for this experiment, we just have 4 procedures, which is the first one, we have to place the food in a microwave. Next, we set the temperature up to 100 degrees Celsius and leave the food about 7 to 8 minutes. And then, record the highest temperature of the food as the initial temperature, and then record the temperature of the food for every minute. So from the experiment, we managed to record at least 10 readings of temperature, meaning that we did the temperature for about 10 minutes. As you can see over here, this is our table of data that we record from the experiment. Then, this is the graph plotted from the data we gained from the experiment, and this graph is plotted linearly. Next, we have table of data from particular solution, where will be explained more detail in a discussion. So we just substitute the time value to find the temperature for about 10 minutes. This is the graph plotted from the equation that we gain from the particular solution.
Comparing both graphs, the experimental data, which is the blue dots, closely follows the black curve, which represents the particular solution of Newton's law of cooling. This shows that the cooling follows an exponential pattern, not a straight line like the right one. Therefore, the theoretical model fits the real data better than the linear approximation.
Starting with step 2, I was asked to find the particular solution of the cooling model. The cooling constant K equal to 0.0321, which was calculated from the data earlier. So, the final particular solution becomes temperature equal to 48.8 exponent negative 0.0321 plus 25. This equation will help us find the temperature of any time. Next, I use this formula to predict the temperature after a long time. I choose T equal to 60 minutes because usually after 1 hour, most hot food is close to room temperature. So, it makes sense to test the model at that point. Substitute into the formula, and then I get to 32.11 degrees Celsius. So, after 60 minutes, the mashed potato meatball temperature is around 32.1 degrees Celsius, which is getting close to the room temperature, as expected. Then, for step 5, I use the equation to estimate the temperature before the first reading. I choose time equal to negative 10 minutes because I wanted to know what the temperature was about 10 minutes earlier. For example, maybe right after cooking or removing it from the oven. Then I substitute into the same formula, time equal to negative 10, and I get 91.67 degrees Celsius. So about 10 minutes before the first reading, the meatball was 91.67 degrees Celsius, which makes sense because freshly cooked food is usually above 90 degrees Celsius. To check if the formula is accurate, I compare the calculated values with the actual temperature readings. The biggest difference was only about 0.8 degrees Celsius, so the model is quite reliable. Then I calculate the percentage error using this formula, and then I get 0.9%. Only this means the difference between predicted and actual value is less than 1%, which shows the model is very close to the real data. I used the Newton cooling model to predict both future and past temperature. I selected the times based on real situation. 60 minutes to see how much it cools, and 10 minutes to estimate its original hot temperature. The predictions are accurate, with a very small error of 0.9%.
In question 3, we were asked if there are any differences between the actual value and the value calculated from the particular solution. Why do you think it is so? So the reason why there's differences is because of the rounding of the calculation. Other than that, it is also due to the heat loss to surrounding because our model experiment is not perfect. For question 4, we were asked what do you think has affected the cooling for your experiment. So there's a lot of reasons, but 3 of our reasons is because of the airflow in the room. Other than that, it's also because of the ambient temperature, meaning that the temperature want to be equilibrium, and the type and material of the container used. For question 5, we were asked what might affect cooling in general. So we think that the surface area of the object might affect cooling in general. The reason why is because the larger the surface area, the more heat can go to the surroundings. Other than that is the temperature difference between the objects and the surrounding. This is because heat tend to go from high heat to low heat. And our third reason is because of the wind or airflow. Wind and airflow can also increase the cooling effect.
For task 2, we'll be using the Newton-Raphson method. From the question, we are given the nonlinear equation to find the root between 0.3 to 0.5. Let's look at the graph. This is the reason why we use the Newton-Raphson method. It's because of the graph is continuous and nonlinear, and it's difficult to determine the root of the graph. Now, let's look where the Newton-Raphson method is coming from. It is from the first two Taylor series expansion equal to 0, because to find the root fx must equal to 0. Then we need to rearrange the equation to let the x become the subject. X is dedicated to the next approximation next to the roots. After generalizing the equation, we will get the Newton iteration equation. First, we need to rearrange the equation equal to 0 because fx must equal to 0 to find the root, and we need to find the differentiation from the fx. Here we get the f prime. We can choose the value as of initial starting from 0.3 to 0.5, which is given from the equation. So right here I'm choosing x equal to 0.4 as its middle of the 0.3 and 0.5. However, we can still use 0.3 as the x initial or 0.5 as x initial, and we still can get the same iteration at the end of the process. We need to insert the formula in the cell, and the x, we need to change it into x initial cell code. Then we need to repeat the same exact step on the f prime equation. Then after we have the initial value of x, fx, and the f prime value, we need to insert the Newton iteration equation under the x column. For example, here C8 minus D8 over E8. And then we just need to drag down all the column to copy paste the equation formula that we just write down just now. In the end, we will be seeing the repeated iteration, which is dedicated that the iteration is already approximately close to the actual root. Right here, we can estimate the root is equal to 0.38947.
In conclusion, for the first task, we applied it to estimate temperature change from minute 1 to minute 10 and calculated its percentage error between the estimated and actual values. For the second task, we solved the equation cosine of 7x minus 1 minus the square root of x equals negative 2x, and the root x approximates to 0.38947. This method proven to be efficient and accurate with a good initial gap. That is all from our group. Thank you for watching our presentation.